Section 3.1.1, horizontal compressions and stretches, and we're going to do some combined transformations. So before we fill this out, let's go to our graphic organizer we filled out the other day. So remember, we have our vertical movements, which are A and our K values, and our horizontal movements, which are the B and the H. So we've already talked about our vertical movements. We're going to really focus on our horizontal movements and then our combined transformations. So remember, when you're graphing the transformations, you're going to follow the order of operations. And so that means we're going to do the B, H, A, and then the K. So your horizontal movements are first and then vertical, just kind of like when you plot a point, you go over X and up or down Y. It's the same idea. So for our horizontal movements, we have to recall that it's kind of opposite thinking. So if we look at our H value, when our H value is bigger than 0, so for instance, if my H value is equal to 3, you would be plugging 3 in for H, it would be X minus 3 moves it to the right. If you have an H value of negative 3, so when it's less than 0, and you plug that in, you get X minus negative 3, so X plus 3, which moves it to the left. So a lot of times students get that backwards. They think that minus moves it to the left and plus moves it to the right, but again, notice that it's opposite because we're plugging in a negative. It's kind of the same thing when you're thinking about your horizontal stretching, compressing. So when your B value is less than 0, it reflects across the y-axis. When your absolute value of B is bigger than 1, it's a horizontal compression by the absolute value of 1 over B. If it's in between 0 and 1, it's a horizontal stretch by the absolute value of 1 over B. So let's go back to some things that we learned last year to kind of help us think about this. So we have y equals the sine of x, and this is graphed from 0 to 2 pi, so that's our first wave of our parent graph. And so what happens if I have y equals the sine of 2x? So if y equals the sine of 2x means that my b value is equal to 2. And so this is going to be a horizontal compression by 1/2. So you notice that this graph has 2 cycles from 0 to 2 pi. And in order to do that, we had to compress it in by 1/2. So there's the first wavelength and the second. So that 2 tells you, again, that there's 2 cycles now from 0 to 2 pi. However, it's a horizontal compression of 1/2 of your parent graph. So if I have the sine of 3x, my b value is now equal to 3, which is a horizontal compression by 1/3. And so now you see you have 3 cycles from 0 to 2 pi. So here's the first one. That's the second one. And then the third. So that means we had to compress it in by 1/3 so that we could have those 3 cycles from 0 to 2 pi. And so that is why it's a horizontal compression by 1/3. And if we look at the next one, now I graphed our parent function, the sine of x, from 0 to 4 pi, so you can see that there are now 2 cycles. And the reason I did that is because we're looking at the sine of 1/2 x, and so now my b value is equal to 1/2, which is a horizontal stretch by 2. So now you notice our graph is half the wavelength is 1 of our parent graph. So in order to get it to be twice our parent graph, we have to stretch it out. And so notice that this new graph, you could fit 2 parent graphs inside of it. So let's go ahead and do some more of this. So first of all, we're looking at given y equals f of b times the x, we're looking at their b values. So stretching it when it is in between 0 and 1 away from the y-axis, compressing it when it is bigger than 1 towards the y-axis, and again, you're changing your x values when you're doing this. So for this first part, we have our parent graph already graphed, so that's y equals the absolute value of x, so that way we can compare it to these new graphs. G of x, notice that our b value is equal to 3, so that is a horizontal compression by 1/3, and I use HC for horizontal compression and HS for horizontal stretch. It's easier than writing it all out each time. So these x and y values that are here are from the parent graph. And so what are we doing to those parent graph values? We're compressing them in by a third. So I'm just multiplying our x values only by a third. So here we have an x value 0, so that stays. And then I'm going to do values that are easily divisible by 3. So I'm going to go to next x value, which is here, which is 3. So 3 divided by 3, or times the third, is 1. And then 6 divided by 3 is 2. And 9 divided by 3 is 3. And we can do that on the negative side as well. So this is an x value of negative 3 times a third gives us negative 1. And negative 6 divided by 3 would give us negative 2. And negative 9 divided by 3 would give us negative 3 for an x value. So notice that our y values stayed the same, but we horizontally compressed our graph in by a third by changing our x values only. And so now I have my horizontal compression by a third. So let's go ahead and look at the next graph, h of x. So our b value is equal to 1/3, which tells me this is a horizontal stretch by 3. So these are parent graph values again. And now we're taking those parent graph values and we're going to be multiplying the x values by 3. So if we start at 0, 0 times 3 is 0. 3 times 1 is going to be 3. 3 times negative 1 would be negative 3. So 1, 2, 3. Oops, that's a little too far over. And then 3 times 2 is 6, and 3 times negative 2 is negative 6. And if we did 3 times 3, we would get 9, and 3 times negative 3 would be negative 9. And so now I have both my graphs graphed. And again, so this second graph, we know that we were horizontally stretching each of my values by 3, so they moved out away from the y-axis. Whereas when we did the compression, it moves it towards the y-axis. So then down here we have our combined transformations, which we've talked about. So remember, we always do the order of operations. So horizontal movements first. So that's our b values. And then this should say h. Sorry about that. So h. Then our vertical movements are second. So that's a and k. And so we have each of our parent graphs, or just functions, or general equations. So notice that for quadratic and cubic, the b and the h are being squared or cubed. For square root or cube root, it's underneath the radical. So again, it's always attached to your x value when you're doing horizontal movements. So if absolute value would be inside the bars and greatest integer inside the bars. And then for exponential, your x is always going to be the exponent. So the b and the h would be as part of the exponent. Rational in your denominator. And then for logarithmic, we have it inside the log. So let's go ahead and just look at single transformations and what each of them are doing. So this first one, we notice that we have negative h of x. It's not inside attached to the x, so that tells me that this is a vertical change. And so for this one, of course, this is going to be a reflection across the x-axis. Because that's your a value when it's on the outside. So when you're reflecting across the x-axis, you're just going to count how far away from the x-axis you are, and then graph your graph. It's kind of hard to draw that half circle there, but you get the idea. So then for the next one, we have h of negative x. So this is inside attached to x, which tells me that's my b value. And so this is a reflection across the y-axis. And so you're just going to count how far away you are from the y-axis. So that's going to be like that. So here we have 1, 2, 3. And then So that would be my reflection across the y-axis. So again, it just looks like you fold in half on the y-axis. Here we have two transformations. This is actually an A and a K because they're not inside with the x there. And again, h of x is just our parent graph. So for my A value, I have a vertical compression by 1/2, and then I'm going to move it up 1. So again, this changes our y values. So if it's a vertical compression, I'm multiplying my y values by 1/2. So 1 times 1/2 is 1/2. And then we have 3 times 1/2 is just 1.5. And then 1 times 1/2 again goes here at 1/2. And then the next one is going to be moving my graph up 1. And so that graph in red would be my final transformation. So the next one that we have here is inside attached to x. So that means that's my h value that we're looking at. So h is equal to -3 to get that plus sign there. So that tells me this is going to move it to the left 3. And again, that's changing our x values when you're doing horizontal movements. So that gives me my new graph, left 3. Then this one is inside with the x, so that tells me that's my b value. So that's a horizontal compression by 1/2. So that means we're going to multiply our x values by 1/2 or divide by 2. So -1 times 1/2 is -1/2, and 1 times 1/2 is +1/2. So that's going to be half that size. Then we have, let's see, 1, 2, 3. So 3 times 1/2 is 1.5. 5 times 1/2, 2.5. And 6 times 1/2 would give me 3. So that's my new graph there. And notice that it is half the size of my parent graph, which means we could actually fit 2 of those inside my parent graph. And then the next one, we have a b value equal to 1/2. So that tells me that's a horizontal stretch by 2. And again, we're changing our x values, so we're going to multiply them by 2. So here I have an x value of -1 times 2 would give me -2. And this would be +2 over here. So that's going to be twice as big as it was before. And then here we have an x value of 1, 2, 3. So 3 times 2 gives me 6. So that's that first part. And then 5 times 2 is 10. So we're actually going to be off our graph. So that looks like 9, 10 would be here. And then 6 times 6 is 12. So 10, 11, 12. So we're just off our graph. So we'll have to just kind of move it out as we can. Okay, so that's just kind of simple transformations because there's not too many that we're combining, but let's go ahead and take a look at a graph where we are going to combine them all together. So it says state the parent function and the transformations made to the parent graph, then graph the parent function and each step of the transformations made to the parent graph. So of course our parent graph, because we have that square root right there, is the square root function. So that's the first thing I'm going to graph on my graph. And so we know what our parent graph looks like. And we can just go ahead and graph that. Then after I graph the parent, then before I do anything, if your b value is not factored out from x, you're always going to want to factor that first. Otherwise, you might get your transformations incorrect. So here, if I refactor that, I get g of x is equal to 3 times the square root. We're factoring out that -2. So that's going to become x minus 4, because we're dividing -2 out from the 8, minus 6. And so had you not factored that out, you might think that your graph is moving to the left 8 when really it's moving to the right 4. So now that I have that, we're going to go ahead and start our transformations. So your b values first. So b in this case is -2, which is 2 transformations. And I always like to do the reflections before stretching, compressing, so that's just a habit. So I'm going to reflect across the, since it's a horizontal movement, so we reflect across the y-axis. Okay, so then the next one that we're going to do is going to be that's 2 for the B, which is a horizontal stretch by 2. So again, we're changing our x values. Or sorry, not horizontal stretch, horizontal compression by half. Oh, because again, it's opposite thinking. So horizontal compression by half. So 0 stays at 0. -1 times a half is -1/2. -4 times a half would be -2. And then 9 negative times a half would be -4.5. And it's a square root, so we would also have the point square root of 16 if it was the x value would be equal to 4. So if I did 16, I would have 8 and 4. I just wanted another reference point for the graph. So now I have my horizontal compression by half, and the next is going to be my h value, which is equal to 4. So that means it's going to move to the right 4, because remember the equation is always x minus h, so that's why h is 4. We're going to move that right 4 by just counting each point right 4. So now we got right 4, so that was our BH. Now we have our A value to do, so A is equal to 3. There's no negative, so I don't have to worry about reflecting it. So that's a vertical stretch by 3, which changes our Y value. So we're going to multiply our Y values by 3. So the 0 as the Y value stays at 0. 1 times 3 is 3. And then 2 times 3 is 6. 3 times 3 is 9. And then, of course, 4 times 3 is 12, so that's going to be off of our graph. Okay. And so the next one's going to be that down 6 because that's our K value. So I'm just going to count down 6 for each of these. And this last graph in orange is my transformed graph. So that would be my final graph with all my transformations. So again, B, H, A, and K. So I want to just go ahead and do one more practice problem. We'll probably do this as an exit ticket or a warm-up or something. So the parent graph of p of x is shown below. We're going to describe the transformations made to p of x and then graph each transformation using a different color. So p of x is this graph in blue here. So the first thing we want to do is, of course, factor out our b value because it's attached to x right now. So g of x is equal to 2 times p, and this would be minus 3x, and of course we're dividing -3 out from 6, so that would be 6 divided by -3 would be -2 minus 4. And so for this, again, you can check. So -3 times x is -3x. -3 times -2 is 6, so that checks our work. So we already have our parent graph, so then we're going to start our transformation. So b starts first, so b is equal to -3, which means we have two different things that we're doing. We're going to reflect across the y-axis first. So just count how far away we are from y to do that. So that gives us a reflection across the y-axis, and you can see you can fold it in half on the y, and it looks, we'll just kind of flip over. So let's go ahead and do the 3 for the b value next. So that 3 is a horizontal compression by 1/3. Again, we're changing our x values when we're horizontally compressing something. So that means I'm going to multiply those values by 1/3. So if I have 3 here, so 3 times 1/3, or 3 divided by 3 would give me 1. If it is on the y-axis, that means your x value is 0, so that's going to stay there. And negative 3 times a third would give me negative 1. And negative 6 times a third would give me negative 2. And then 7 would be about 2.3. So somewhere in there. And then we just got to connect our lines. All right, so now I have that, and I can go ahead to my next value. So that's my B. Now I can do my H. So H is equal to 2. So that's going to be moving my graph to the right 2. So I would just count over 2 for each one. So that'd be there. And so that's my graph moved to the right 2. My A value is equal to 2. So since my A value is 2, that's a vertical movement, so it's a vertical stretch by 2, because those make sense. So that's changing your Y values by 2. So all my Y values I multiply by 2, so this going off the graph in blue, so this is a Y value of 1, so 1 times 2 is 2, so that's going to go to here. It's a Y value of 0, so that stays. And we have a Y value of negative 3 times 2 would give me negative 6. And this one stays. So I'm just going to get my ruler now. And that is my vertical stretch by 2. And the last one's my K value, which is negative 4, so that moves it down 4. So now all I have to do is just count down 4 for each one. It's a little off there. Okay, and that's my graph moved down 4. So now I've done all my transformations. So again, as you can see, it's really important to follow the order of operations when we're doing this. Make sure you factor out your B value, and then again, you can always use that graphic organizer to help you with what each of the different values are doing.